I'm going to start with a question. There are three particles that make up the atom. It's the electron, the proton, and the neutron. Which of these particles are found in the nucleus? We'll give you some choices. Now, of course, you know the answer to this. Chapter 30 starts with a review of atomic structure, and you're already familiar with the fact that the nucleus of an atom is made up of protons and neutrons, and then they're surrounded by a cloud of electrons. But here's a question. Protons are positively charged. We know that positively charged particles repel each other, so why doesn't the nucleus just blow itself apart? Well, in fact, sometimes it does, as we'll talk about today. But there's another force at work, and something else we talk about in Chapter 30 is this. There's a strong force at work in the nucleus that holds the particles together. And in order to have the nucleus be stable and not fall apart, you have to have the right blend of protons and neutrons. And so, as we discuss in the chapter, there's only certain possible combinations of protons and neutrons that are stable. There are other combinations that you can make, but they're not stable. And when you have combinations of protons and neutrons in the nucleus of an atom that will hold together but aren't stable, those are atoms that we call radioactive. And I have an example of some radioactive atoms right here. Actually, I'm going to start with this little teapot. And this little teapot has uranium oxide to make the glaze. And this was used in the 1920s as a very common glaze, uranium oxide, because it makes this lovely orange color. It's very, very popular. But uranium is an atom that is so big that the repulsive force between the protons can't be stabilized. And so at some point, a uranium atom will fall apart. Now, this is a particular isotope of uranium called uranium-238. In the chapter, we review the meaning of an isotope. The number of protons in a nucleus determines the element. The number of neutrons determines what isotope you have. So this teapot is glazed with uranium-238, and it's actually uranium oxide. But the 238 tells us that there are 238 nucleons, that is protons or neutrons in the nucleus. The 92 tells us that there are 92 protons. So 92 protons, 146 neutrons. There are more neutrons than there are protons. And heavier atoms have more neutrons than they do protons. But these uranium atoms fall apart. Now, they don't fall apart very, very rapidly, but every once in a while, an atom will indeed fall apart. And so if I bring a Geiger counter up next to the teapot, you can hear the clicks. It's detecting the radiation emitted when the radioactive particles inside this teapot decay. And over here, I have glassware. And this is glassware which has uranium in it as well, which gives us this lovely green color. It's also fluorescent. And this glassware is also radioactive for the same reasons that the teapot is. It's got uranium in it. And uranium is a nucleus that is radioactive. Now, when the uranium atom decays, its first stage is this. It decays by the emission of an alpha particle. And an alpha particle, as you'll learn in the chapter, has 2 protons and 2 neutrons. So it's got 2 protons and 4 nucleons. So we can make an equation that's the equivalent of a chemical equation, except it works with nuclei, and we can balance superscripts and subscripts. Here's the question for you. What's left over after the uranium sheds an alpha particle? What nucleus are we left with? We'll give you some choices. Well, it's uranium-238. 238 on the top, 92 down below. It loses 2 protons, so it turns from atomic number 92 to atomic number 90. 238 up top says 238 nucleons, but it loses 4 nucleons, so we're left with 234. So it turns into atomic number 90, isotope 234, that's thorium-234. Now, thorium is itself radioactive. When uranium decays, it just starts a chain of decays that goes on for some time. So it decays into thorium, and that decays, et cetera, et cetera, et cetera. And in the chapter, we have an illustration of a decay chain of one of these very heavy but unstable isotopes. Now, we detected the presence of uranium, which is radioactive, not by looking for its daughter nucleus, not by looking for the presence of the thorium that it decayed into, but by detecting the thing that it threw off. When it decayed, it threw off an alpha particle. And an alpha particle, Well, an alpha particle has 2 protons, 2 neutrons. So an alpha particle is just a helium nucleus. 2 protons, 2 neutrons. It's a nucleus of a helium atom. Now, helium isn't scary, but a helium nucleus that's an alpha particle is, and it's scary because it's traveling at incredibly high speeds. When a nucleus falls apart, there's a tremendous amount of energy given off, and it mostly turns into energy, kinetic energy, of the emitted alpha particle, which flies off at a tremendously high speed. And that's how we're able to detect the presence of the emitted particles, because they're traveling at such high speeds they tear electrons off of atoms and they leave ions in their wake, and we can see that in the cloud chamber. The cloud chamber is cold on the bottom, it's warm on the top, there's isopropyl alcohol vapor inside. At some point it reaches the dew point, and right there it wants to form little droplets of isopropyl alcohol. And it will if the cloud is seeded by something. There's something to initiate the condensation. What initiates the condensation, what starts the formation of a cloud, is the passing of a charged particle. It leaves a trail of ions, and on that trail, a cloud will form. And so where you see little clouds in this chamber, you're seeing tracks from the passing of an alpha or a beta particle. But now let's actually put in a source of radioactive atoms. I'm going to put in an alpha emitter inside the chamber. And when I put in the alpha emitter, you can see a dramatic increase in the number of clouds that we see, and they're also thicker. Alpha particles are very, very highly ionizing, and so they leave very thick, puffy clouds in their wake. Now, when radioactive atoms decay, when they fall apart, they do so in a very mathematically predictable way. And that's something we'll talk about in the next segment.